Hello everybody, I'm back with another video on equilibrium concentrations and how to find them using what I call the dice method, where you have you figure out the direction of the reaction first and then use what's often called the ice method, where you use initial change in equilibrium considerations. It's a systematic way of figuring out composition of a system. It could be in concentration or it could be in partial pressures. We did one last time in partial pressures. I'm going to make a few videos like this where I work some problems. With every problem, I'll try to make it where it has shows a new trick, if you will, or something important to take note of. So I just made up kind of something with some numbers here. A system, it's in the gas phase again, where we've got, I don't care what it is, I'm just going to call it A2. It's some sort of gas phase molecule. It has, it's something like, it could be like Cl2, something like that, but I just wanted to put some idealized numbers down, going to 2A in the gas. So it's doing some kind of decomposition. It's I stayed at 500 degrees Celsius. It has a Kc. So we're dealing with molar concentration now, which you can do in the gas phase. In gas phase, you can do partial pressures or molarity. Really small value for Kc. It's 10 to the minus 13. And that's very possible. They get to be very small. You know, like for example, the autoionization of water from H2O liquid to H plus and OH minus, that equilibrium there, it's often denoted Kw, but it's just like Kc, is 10 to the minus 14 at room temperature. So there's nothing unrealistic about this type of an equilibrium constant. So A2 has an initial concentration of 2.00 times 10 to the minus 3 molar, and this is 0 initially. So it's another problem. Again, the reaction quotient Q sub C would be products A squared over A subscript 2, and this would be, again, 0 over a number, 2 times 10 to the minus 3 is still 0. So the thing is that this is a no-brainer. Again, it's going to be pushing to the right, but I'm going to definitely work a case in the future where it goes to the left that as well. I just want to show another scenario here, if you will, that's a little different than that. I'm going to try to, every problem I do, I'm going to try to highlight something different about it. So let's set up really quickly. Our direction is we're going right towards products until we get to our equilibrium composition. Let's make a little table here. I'll put it off to the side here. Let's say we have, I want to make it similar to the notes. We have A2 in molarity, and then we have A in molarity. So initially, the I we have for this species A subscript 2, 2.00 times 10 to the minus 3 molar. But we have a big old 0 here for the species A. Here's a key step here. So the change step, put a little asterisk, people tend to make a mistake here. We're losing X, but unlike the last problem, there's 2 of these. It's every time you lose 1 A subscript 2, you pick up 2 of the A's. So it's 2 to 1. So that's going to be a plus 2x. Right there is where people tend to make an error. And then the equilibrium step, if you want to call it that, is just bring it on down. 2.00 times 10 to the minus 3 minus x. And this is just going to be 2x. We're good so far. So now QC has exactly the same form as KC. And I'll write down it's 1.00 times 10 to the minus 13, tiny number, is equal to, we're going to have in the numerator A squared, right? So here's another point where people make a mistake, is you have the 2x, and for some reason, so we've got A, and then we're going to have a 2x up here. They don't square it. If they've already got the 2, they for some reason forget the 2 that goes to the square of the thing. I'm not sure why. Or sometimes they forget both. They just put x in the numerator and so forth. But that's a very common mistake. Like when I observe tests, I see that all the time. So then the next step is we have in a denominator, it's just to the 1 power, so it's 2.00 times 10 to the minus 13, minus 3, excuse me, minus x. We have a 13 over here and a minus 3 over here. And that's great. Now, you can solve this out quadratically. You're going to have a 4x squared term in the numerator. You're going to have a term that is to the x to the first power when you cross multiply, and you're going to have a big old number here. But the thing is when you have a tiny equilibrium constant, I will say for all practical purposes, if it's less than 10 to the minus 5, if it's less than that, we can make this approximation. On exams, I will make statements like you can use the small x approximation. I'll show you what that is in a second. Also note, you do not have to use it. You can do this out quadratically. It's just that it will take you 15 minutes, unless you have some kind of specific solver on your calculator, as opposed to 2 minutes, and it lends for more error. If you're unsure, don't use it, and I will provide a rule set, we'll call it a guideline that we'll use in this class. Is it something that could vary by opinion? Sure. Different books might have slightly different guidelines. I'm using a guideline very similar to most Gen Chem books because it keeps your error on the order of a couple percent, or if that. And so in this problem, what you can do is if you're having such a small equilibrium constant, it means that your initial concentration of this species is going to be a larger number relative to the amount that leaks out and goes to product, because you don't need much of it. It's a tiny amount because the equilibrium constant, which is products over reactant, suggests it's a tiny amount of product compared to the original stuff you have. And so this number here, and if you don't know what it is, solve it out and get what x is, and you'll see that it's very similar to what I solved for at the end. You can totally do this out quadratically in long form and verify how accurate your value is that you get from the estimate. So the estimate is like this. Put a little squiggle there like it's approximate. So you got the 2x squared, don't forget the square. And then you're going to get rid of that x there. And that's the term, subtractive term. So that makes the math a lot easier. Now it's no longer quadratic. It doesn't have an x. And that's going to be just by itself. So what you can do is set up, you can solve this and get it to the point. You do 1 or 2 steps of algebra. X is equal to 1.00 times 10 to the minus 13. You're going to multiply that by 2.00 times 10 to the minus 3. You squared this up top, so you got a 4. And all that will be, you can write the square root symbol. I just like to write it to 1/2. And so what you get for this is x is equal to, I just want to make sure you can see it here, it looks good. X is equal to 7.07 times 10 to the minus 9. This will have units of molarity. It's a tiny number. It's a fraction, it's a tiny fraction of this number here, the initial concentration, which is 10 to the minus 3. If you do this out quadratically, you're going to get a number very close to this number. Verify it for yourself if you don't believe me. If you don't want to do it all out, you could probably give these numbers to an AI and it can run it in several seconds for you. So that's the first step. And let's, I want to just go through this. We're not done yet. I have to get my eraser. 1 second. So what do we have here? We're looking pretty good so far. Well, I don't want to erase everything. I'm just going to erase this over here. Well, I actually need that. So let's go through this. When we go through this, That's giving us x. So some of the concentrations that we have, let's see here. We have a subscript 2. That's going to be, wrote that wrong. The concentration of species A sub 2, species right here, is going to be 2.00 times 10 to the minus 3 molar minus 7.07 times 10 to the minus 9. That's 6 orders of magnitude, so smaller. So that's going to be the same number to the sig figs that are any that are reasonable. I mean, that's the same number basically. You're subtracting something 10 to the minus 9 off of something that's 10 to the minus 3. So understand the goodness of the numbers. That's why we spent a little time talking about sig figs last semester. Let's get the concentration of just species A itself, and that's simply going to be 2 times this value, 7.07 times 10 to the minus 9 molar, and that's 1.41 times 10 to the minus 8 molar. So these are the two concentrations of interest. Let's go through and verify our results. That's really like the DICE method should have. If I can come up with a good abbreviation, a final stack, because you can check your work. So KC is going to be A squared divided by A subscript 2. And so let's put in our values here. For A squared, we're going to have 1.41 times 10 to the minus 8 squared. That's an 8. And don't forget the square. And then A subscript 2 is going to be 2.00 times 10 to the minus 3. When I plug that in my calculator, I get, let's see here, 1.00 times 10 to the minus 13, unless it's an equilibrium constant. And that's what we started out with, right? So we look good. So that matches our KC that we were given. On roughly page 21 of the notes, I talk about some specifications of what I will give on exams and so forth, so you can feel confident that you don't have to struggle too much. You just know how to do these calculations, no tricks. So let's go through that really quick. All this is written in notes. I'm not going to rewrite everything on the board. Just go back and says from this class on tests. First place is you could always, you could have a problem like KC is x to the fourth, 3 minus x. I mean, you could have a problem all day long that has a power greater than squared, right? We're not going to go beyond quadratic. There is a power, I think it's either the fourth or the fifth order polynomial that there is no analytical solution for, and even a cubic. Let's say this is to the fourth power. Let's say it was a cubic equation. If I wrote down as a number here, we got an x cubed, we got something else, we got x squared plus 2x plus, a number, I'll just say 4, I'm just making something up. Solving a cubic equation by hand is a nightmare. On the other hand, in real world, what we would do is we take a cubic that provided it has real roots, or at least a real root, 1. And I do this all the time. I teach a course where we solve a formative van der Waals equation. We end up with cubics, and I don't tell people to do it by hand. We put it in a computer program, we solve it, or use Wolfram Alpha. So, we're not going to have access to the exams. We do know when you do with higher level roots, higher level polynomials, which you could very well find in a real equilibrium question, you would use a computer-based or graphical method or something like that. And also know that above a certain power, there's no analytical solution. So it's not a matter of you not knowing math. You do need a computational tool to solve it. So I won't give anything higher than a quadratic. So know how to deal with these like x squared type of problems. Know the quadratic equation. If it's quadratic, you can always use it, but there'll be times when you can use the small x approximation. So you can always use it. So you can always use the quadratic. You don't have to make any approximations. Some people tell me they have solvers. Really don't care if you use it as long as your input is good and you know what you're doing. I'm happy with that. So I'll say don't do the small x approximation. I guess somewhere in here is a hyphen, I guess. Approximation for large k's, because that tells you that minus term is going to be significant when you're going to the right. I will make a rule of thumb. It's based on personal knowledge, the concentration ranges that people usually set experiments up with. We don't start out an experiment with little teeny amounts of things when we're doing something. I will say this is a rule of thumb for us, is if your k is greater than 10 to the minus 4, don't use it unless I say to use it. Don't use the approximation. The problem we did the other day that had a k that was something, I forgot, it was like point something, like 0.3 or 0.4, the one we did in the prior prior video, that's too big. That you had to do out quadratically. Sometimes k is a real big number, like tens or hundreds, or more. Definitely don't use it then. You're misunderstanding when to use it. When you're between 10 to the minus 4 to 10 to the minus 5, I'll say this. What you can do is take the x value that you solve for by using the approximation. All this is written out in the notes. You solve for x using the approximation and then check it relative to the initial concentration multiplied by 100. That should be, I'll put a dot because we got a lot of x's here. And if it's less than 5%, you're good to go. The approximation's good. If it's greater than 5%, you're not. That sounds good. That's easy. That's really easy to forget on an exam. I will usually, for borderline cases, put on there you can use a small x approximation. Where really I would never contrive a problem to with ridiculously low concentrations of partial pressures. If it's less than 10 to the minus 5, I would say use the approximation. You're welcome not to. You don't have to. You can do it out quadratically, but do a couple of them that have a small number like the one we just did, 10 to the minus 13. Do it out with the shortcut. Do it by hand and compare it to 3 or 4 sig figs difference. It'll be negligible. It'll be within 1% or so of each other. And I say this because you say, well, it's just one quadratic. When we get to the chapter on aqueous ionic equilibrium, we spent a bit on titrations, particularly with the weak acid with a strong base and the weak base with a strong acid. In those cases, sometimes in the titration, we would have to solve multiple quadratic equations. And it's like, wow, I don't want to keep doing this every step. This is will give you a really quick shortcut of the way of solving the problem, and not make mistakes, because you got something. And usually there with these weak acids and weak bases, usually Kc or the equivalent to Kc will be a small enough number where it's either justified or I'll give you clearance to do it, because it's still not that big of an error anyway. It's maybe 5-6%. So at any rate, the rule sets are in the notes. If that's a little complicated, you can always fall back to the quadratic. But for very small numbers like we did today, it's a big time saver if you don't have to do it, and you don't get any more benefit out of it. Saying I know it 8 places behind the decimal does not mean anything if you're starting out with inputs of molarity to 2 or 3 sig figs, or pressures to 2 or 3 sig figs. It's like, you're not like we had before here. We were subtracting off a number that was, I forgot what it was like 10 to the minus 9 from something from 10 to the minus 3. you know, I mean, it's the answer it doesn't change the original number. I mean, you have something many orders of magnitude smaller than what you your input was. So, you know, this is getting the idea of the goodness of numbers that we work with, and you're always welcome to do it out in long form if you want to. I'm going to do another example or so in the next video, and then we'll be wrapping this chapter up pretty quick after that. This is the, it's easy to do. The math at the level of the quadratic equation. I just find that there's certain population of students that just have an immensely hard time with this. I don't know if it's a math issues or lack of practice, but work as many of these as you need to. Work the problems in a skill builder. I have an ICE skill builder unto itself. There's problems built in notes. Rework all the ones I do. And if you want more problems, a good thing to do is cut and paste my problems and put them in chat and tell it you're a Gen Chem student. You want to see all the steps. You want to see units, yada, yada. Any convention I use, if I call it K sub C, they might call it KEQ for something different. Tell it what I call it and have it generate your problems. Tell it, you know, I want one with this, you know, we did one with no products, only reactants. Give me one that's opposite of that or something like that. And we will do something like that. But I'm just saying, you know, you can generate problems. You can get a book. Although, honestly, in this day and age with AI and things like that, you know, you can train the AI once you get going on a conversation with it. You retain it to be more productive than it is when you just walk on it the first time. So if you get a good chat going, and you're talking about something like equilibrium, keep it alive and off to the side. It's a great resource, way of generating problems. Because just like I make mistakes, textbooks have mistakes all the time. There's nothing sacred about any general chemistry textbook. They're just, to me, sources of problems. So on that note, I hope you got something out of this video. We talked a little bit about equilibrium calculations with the small x approximation. Try this problem without the approximation and compare your answers. If I am wrong, tell me. On that note, have a good day.